In this video, we discuss the intermediate value theorem, and we show some examples of that. And then we also discuss the bisection method for finding zeros. So here's a statement of the theorem. It says if f is a continuous function on the interval from a to b. So we can graph the function from a f of a to b f of b without lifting up our pencil. And f of a is not equal to f of b. So you've got two distinct values, and k is some number in between them. So if all three of those things are true, then there's at least one number c in the interval from a to b such that f of c is equal to k. Or in other words, f of x equals k has a solution on that interval. We'll use this theorem to show that equations have solutions. We can also use it to find zeros. And we'll talk about examples when the intermediate value theorem does not apply as well. So let's look at this one. This one's a sort of a typical textbook example. It says, use the intermediate value theorem to show that x squared minus or plus x minus 1 equals 11 has a solution. Well, obviously, this function is our f of x, and this is our number k. And we just have to verify for ourselves that f is continuous on the interval of interest, that f of a and f of b are not the same, and that k is some number between f of a and f of b. Now, we're not actually given an interval in this particular problem statement, so we have to come up with an interval ourselves. But our goal is just to choose an a and choose a b so that f of a and f of b are on either side of k equals 11. So first of all, let's talk about this first statement. It says f is continuous on the interval from a to b. Well, yes. I'll say since f is a polynomial, it's obviously continuous on the entire real line. I can plug in any x value I want, and I'll get out a number that makes sense. And I need an interval from a to b. I'm just going to pick any a value I want. I'll just substitute 0. F of 0 is 0 squared plus 0 minus 1, which is -1. And now I want to choose another value for x to be my b, and I want to choose b so that f of b is larger than 11. It's basically what we're looking for is this. I know my function passes through that point, x equals 0, y equals -1. And I'm interested in y equals 11. So I know that the graph of f of x is actually a parabola, but I want to show that that parabola like passes through the line, the horizontal line, y equals 11 somewhere. So I need to pick an x value over here where I'm pretty sure that this f of 1, or excuse me, f of whatever that value is, will be greater than 11. Well, if I plug in 2, I get 2 squared plus 2 is 6, or 2 squared is 4, 4 plus 2 is 6, 6 minus 1 is 5. That's not going to get me where I want to go. Then we'd be showing that, well, on the interval from 1 to 2, we get 5 here. And the function is continuous, but it doesn't pass through that line y equals 11, so we haven't gone far enough. We need to choose an x value that gives us a y value that's larger than 11. So I could try 3. 3 squared is 9. 9 plus 3 is 12. And 12 minus 1 is 11. Oh, that's exactly right. There's the solution. Okay, so we've got that. Maybe typically we wouldn't get that lucky where we would just choose the right value of x. Let's look at f of 4. So 4 squared plus 4 minus 1. That's 16 plus 4 minus 1. That's 20 minus 1, which is 19. So when x equals 4, y equals 19. And this is, of course, not to scale. And so my graph roughly looks like this. Now this is not to scale at all. So it's supposed to be a parabola. Yeah, gonna be something like this. Maybe I don't know. I'm just guessing. That doesn't look right. Maybe I should graph this on a graphing calculator. But the idea is I know that the function passes through this point, and I know that the function passes through this point. And even if I didn't know that it was a parabola in between, even if it looked something like this, then I would know that there's at least one x value in the interval from 0 to 4 that gives me a y value of 11. And it turns out that x equals 3 works. And I just sort of stumbled upon that. 3 squared plus 3 is 12. 12 minus 1 happens to be 11. This is obviously not what the graph looks like. It's a cartoon. But I hope that that illustrates the concept. So the concept just says that if I pass through this point, if where x is equal to 0, then y is equal to -1. And my graph passes through this point, x is equal to 4, y equals 19. Then there has to be some x value in between that gives us the right y value, that y equals 11. We don't happen to know what that is most of the time. We happen to have stumbled upon it in this example. But the theorem says that as long as our function f is continuous, the function will take on all of the values between -1 and 19. So I guess I'm trying to use the theorem to show that this has a solution. So I said f is a polynomial, so it's continuous. That part checks out. And then we've got f of 0 is -1 and f of 4 is 19. And then we have to say this part. Obviously, those are not the same. F of 0 is not equal to f of 4. And we need k to be a number between f of a and f of b. So we need 11 to be between -1 and 9. Or 19, excuse me. And that's true. Since all of those things are true, but continuity, 2 function values that aren't the same, and our k value in between those function values. And by the intermediate value theorem, f of x equals 11 has a solution on the interval from 0 to 4. That's it. So we've just used the theorem to show that that equation has a solution. Now I know that particular one we could have solved by hand. It's just x squared plus x minus 1 equals 11. So you could subtract 11 from both sides. You'd have x squared plus x minus 12 equals 0. We'd look for 2 numbers that give us a product of -12 and a sum of 1. Which means our 2 numbers have to have a difference of 1 and a product of 12. So 3 and 4 will work as long as the 3 is negative. -3 plus 4 is +1. -3 times 4 is -12. That means those numbers go here and here. And the equation has this solution, actually 2 solutions. X equals, this product equals 0 when either the first factor equals 0 or the second factor equals 0. So either x is equal to 3 or x is equal to -4. If we add the 3 to both sides there, subtract the 4 from both sides. If I graph this, well, what do I know about my graph? I'd like it to be to scale now. Actually, let's graph this one. We have f of -1 is equal to 0. F of 4 is equal to 19. And you keep going. It's kind of a pain. 19 is like way up there. But the point is that graph crosses the line y equals 11. The graph of x squared plus x minus 1 crosses the line y equals 11 at two values, at x equals negative, or x equals 3 and x equals negative 4. And by symmetry, since this is 3 units in this direction and 4 units in this direction, the vertex must be halfway in between. So probably at x equals negative 1. And we're going to see something like this when we substitute in negative 1 here for x. F of negative 1 is equal to negative 1 squared plus negative 1 minus 1. So we've got negative 3 there. And my graph is going to look like this. And I knew that it would roughly look like that because of the symmetry. And I know it's a little bit hard to see because of the way I've drawn it. It's not to scale. This is 4 units and that's supposed to be 3. Yeah, we didn't even need to graph that to know that the equation had a solution. The intermediate value theorem says that as long as this function is continuous and our function takes on two values that are on either side of 11, then the graph has to cross the y equals 11 horizontal line. And if it has to cross there, that means that there's a particular x value on the interval like between those two x values that gives us the right y value. Now, if you're saying to yourself, are there any examples where the intermediate value theorem does not apply? I think it's easy to see. Let's say we had a graph that looked like this, like a piecewise function. So maybe that's 4, and that's y equals 1. I'll make that 4 as well. And let's call that 8. And draw a parabola facing up from there. Oops, put an open circle there so it's a function. Now let's say we're asked this question, does the intermediate value theorem apply to f of x, y equals f of x, where this is y equals f of x, on the interval from, let's say, 0 to 5. And you probably say no, because x equals 0 is right here and x equals 5 is over here. And there's a gap. The function's not continuous. It's continuous on this interval and it's continuous on this interval, but it's not continuous at x equals 4. This is what we call a jump discontinuity. You've got a different limit from the left than you do from the right. And in this particular example, we skip a whole bunch of y values. So if someone asked me to find the solution, let's say they said, if possible, show that f of x equals 6 has a solution on the interval from 0 to 5 using the intermediate value theorem. You'd say, well, let's look at f of x equals 6, or excuse me, the graph of y equals 6. Well, does that ever cross the function f of x? It doesn't. We skip those values. We skip all of the x or all of the y values between 4 and 8 because our function's discontinuous. We actually get all the y values between 1 and 4, not including 4, but including 1. And then we have all the y values from 8 to infinity, but we skip these right here in between. So it's actually not possible to use the intermediate value theorem on that interval. And we would say so. Solution, or I guess the answer to this short answer question, is it is not possible to show that f equals 6 has a solution on that interval. Because f is not continuous on that interval. And we can be specific, it has a jump discontinuity at x equals 4. So we're skipping some y values there. Now we could have drawn it so that the intermediate value theorem didn't apply, but the function actually did have a solution on that interval. We could have drawn a different picture so that the theorem wasn't appropriate, but the function still had a solution. We could have done that as well. I'm not going to look at that case here, but the point is we can only use the intermediate value theorem if all of these things are true. F has to be continuous on a particular closed interval from A to B. F of A and F of B have to be two numbers that are different from each other, and K has to be in between those. Provided all of those things are true, then f of c or f of x equals k has a solution on that interval between the two x values that you started with. And I think it's easiest to see graphically. Here's a f of a, here's b f of b. We know that the function goes from that point to that point somehow. And since it's continuous, you can draw some kind of curve that gets you from here to here. I mean, it might be that one, could be that one, it could be that one. There are lots of possibilities for how the function can get from there to there. But the theorem says that if the function's continuous and you can draw it from that point to that point without picking up your pencil, then you get at least one x value that maps to that y value. This c goes with this particular function. Obviously, that function would have a different value of c, it would have this value of c. Call that c sub 2. And then this function would have a value of c that's way over here. So c sub 3. But in any case, with either of these three functions, we always get at least one value of c. Now I could have drawn it like this. Here's a f of a, and here's b f of b. And I'm having a tendency to make the function these two values, this one smaller than this one, but you could have just as easily drawn it the other way. I mean, you could have done like something like this if you wanted to. Then if I said, this is my k value, that k value crosses 1, 2, 3, 4, 5, 6 times. So there would actually be 6 x values on the interval from A to B that would all map to the same y value. The theorem just says that we get at least one of those. Because if it was just a line segment, that line segment would cross through or would pass through the horizontal line y equals k at least once. But we could draw some more interesting curves that have a lot of hills and valleys where that function might cross that horizontal line more than one time. Okay. So that's an example. Let's look at another example. All right, so this one says, use the intermediate value theorem to show that this polynomial is equal to 4 at some x value on the interval from 0 to 3. So we can call this our f of x. And we can choose that to be our value for k if we want to. And we're told that, or we're asked to use the theorem to show that that equation has a solution on this interval. So we just first state that f is continuous on the interval from 0 to 3. Of course, it's continuous on the entire real line, since f is a polynomial. And in this problem, they actually give us the interval of x values. So they want us to evaluate f at 0. So we plug in 0 here for x. We just get -2. If we substitute 3 for x, we've got this here. So that's 27 minus 9 plus 3 minus 1. That's 18 18 plus 1, which is 19. And our y equals 4 is in between -2 and 19. So all of the conditions of the intermediate value theorem, the function's continuous. Those two y values are different from each other. Oops, that's a 3. And then the y value that we're interested in is y equals 4. Well, I think it's pretty obvious. If I've got a curve that is continuous that goes from this point to this point, it's going to have to cross that line at least one value, at least one point. Now, if we wanted to, we could actually solve that equation for x. Since it's a polynomial equation, we actually know how to solve it. But it might be easier to just look at the graph on Desmos.com and view this, solve it graphically. So let's do that. Okay, so this is our function. For example 2, we have x cubed minus x squared plus x minus 2. That's a cubic polynomial. I changed the window here of x and y values just by going to this little wrench and then using this and then this to type the lower limit for x or the lower and upper bounds for x and the lower and upper bounds for y that we were for the window that we were interested in. I knew that we were trying to look at the solutions to the equation f of x equals 4. So I plotted the horizontal line y equals 4. And then I wanted to view the values of f of 0 and f of 3 on our graph. So I evaluated the function f at x equals 0. We did that on paper as well. We know that when x equals 0, y is equal to -2. And when x equals 3, y is equal to 19. And we know that y equals 4 is in between that 2 and that 19. If we want, I guess we could also graph y equals 2 or -2. And y equals 19. So basically, I'm just saying that my function is between those two horizontal lines. Oh, goodness. Okay, so my y's are in between those two horizontal lines. There's my f of 0, and there is my f of 3. And I've got this green dotted line is x equals 0, and that green dotted line is x equals 3 over there. So we're here in this window where our y value of interest is y equals 4. And we're drawing this continuous curve. And we're saying, okay, if our y value is between this -2 and the 19, and it is, and the function is continuous, well, then there has to be a solution to the equation on the interval from 0 to 3. So somewhere between the two green horizontal lines, or excuse me, vertical lines, we have to have a solution. And I plotted those points there and there on our curve. want to get rid of those lines to make it simpler. We can see our curve, see those 2 points, and we see that this line crosses here, and there is a point of intersection. It looks like x equals 2. When x equals 2, y equals 4 on that graph, or f of x equals 4 has a solution of x equals 2. If we want, we can confirm that. Let's just graph x equals 2, and we see that x equals 2 and the y equals 4 both cross at that location 2, 4. So that is sort of what we would expect. But this theorem actually doesn't tell us what the solution to the equation is. Like, we had to look at the graph to infer it, or we could just solve the polynomial equation using the methods that we've already studied. So let's look at the piece of paper and see if we can't do that by hand. But the theorem does guarantee us that there is a solution there. So there exists a C on the interval from 0 to 3, such that f of C equals 4. Or in other words, f of x equals 4 has a solution on the interval from 0 to 3, and we're pretty sure that the answer is 2. We can figure that out if we solve this polynomial equation. To do that, we'll subtract 4 from both sides. You might say, okay, well, when does that polynomial equal to 0? Well, I'm not sure. If I knew how to factor it, I would. But we can't factor by grouping. If we group these together, we factor out an x squared. We're left with an x and a 1. If we factor out an x squared from this, a negative 1. And there's not really anything to factor out here. If I factored out a 1, I'd still have an x minus 6. So factoring by grouping doesn't work here. For this, to solve this equation, we might use what's called possible rational roots. This is actually a technique that we use a lot in differential equations. The possible rational roots, or and remember, roots are the x values that cause that function to be 0, are given by the factors of the constant term. In this case, -6, divided by the factors of the leading coefficient. And the leading coefficient there is a 1. So we've got plus and minus 1 and plus and minus 6. 1 times -6 is -6, -1 times +6 is 6. That's why we get the plus or minus there. Plus and minus 2 and plus and minus 3. And then you divide by plus and minus 1, which doesn't actually change anything. So the possible roots of this function are these. Or the possible rational roots of this function are given on this list. And you just sort of guess. You sort of look at this list and you say, okay, what could I plug in here that might give me a 0? And if I substitute 1, I'm pretty sure I'm not going to be able to get rid of that 6. I have 1 minus 1 plus 1, minus 6. So we're going to end up with a -5. That's not a 0. So we'll just do f, or not, that's not f, but this function evaluated at 1. So that's not a root. We could substitute -1, but I don't think that's going to help us at all. That gives me -1, -1, -1, -6. Well, they're all negative now, so it's definitely not equal to 0. So that's not going to work. I'm going to skip the 6s for now. Let's look at the 2s. I like to stick to small integers if possible. So 2 cubed minus 2 squared plus 2 minus 6. So that's 8 minus 4 plus 2 minus 6. 8 and 2 is 10. -4 minus 6 is -10. So we're going to get a 0. So that works. So x equals 2 is a root. Or in other words, one of the solutions to this equation is x equals 2. Now, since it's cubic, it also has two other solutions. They may or may not be complex, but in this question, we're really concerned about finding or showing that this equation has a solution. The theorem already allowed us to show that the equation has a solution. We were just looking for the particular solution. And it looks like we found it. When we substitute in x equals 2, we actually get 0 for this. That means if we substitute in x equals 2 here, we get 4. And if you're not sure about that, you can always plug in f of 2, or 2 to x, f of x, which was this original function. And we get 8 minus 4 plus 2 minus 2, which is 4. So that is the solution of the equation on the interval. All right, so that's sort of an aside. It's just a good opportunity to practice solving polynomial equations and using possible rational roots list to solve the equation. We can also use the intermediate value theorem to show that a particular function has a 0, or in other words, it has an x value that causes the function to be 0. We're going to use the theorem here to show that this particular function has a 0. And we'll look for an interval of interest as well. A and B aren't given to us this time. And then we're going to use what's called the bisection method to find the 0. To give us a sense of where to start, it's helpful to sort of think of this as, think of this in a different way. I think I'd like to take that e to the 3x plus x, which is set equal to 0, and subtract the x from both sides. So I've got an exponential function and then a linear function. I don't know what this function looks like off the top of my head, but I know what the exponential function looks like, and I know what y equals negative x looks like. So I can graph those. 2 times e to the 3x looks like this. When x is equal to 0, y is equal to 2, and then it has that shape that we're accustomed to for exponential functions. And y equals negative x is just a line with a slope of -1. And so I know that I would expect my 0 to be the point of intersection of those two curves. Or in other words, the x value that satisfies this equation is the same as the x value that satisfies this equation, and the x value that satisfies this equation is called the 0 of this function, where f of x is this sum of the exponential function and the linear function. And so we want to find that x value. We want to find c. And first we want to show that that equation has a solution. We can see graphically that it has a solution, but we want to show that it has a solution using the intermediate value theorem. So I'm just going to pick a couple of x values for my a and b. I need to choose an a and b that are on either side of this c. I don't actually know what c is, but I'm just going to choose some negative number over here, and then I think I'll just choose x equals 0 over here. So let's evaluate f at, let's say, -2. We've got 2 times e to the 3 times -2 minus 2. So I've got 2 e to the -6 minus 2. And I don't actually know what that is without a calculator. So I'm going to use the graphing calculator on Desmos to compute that number. And then we'll look at f of 0 as well. We've got 2 times e to the 0 plus 0, which is just 2. So I need my, I need this number to be negative in order for us to show that this function passes through the x-axis at some value. This picture tells us the equation has a solution, but this picture is going to be sort of more telling for what we're interested in. When x is 0, y is 2. And when x equals -2, that y value is something, and I don't know what it is. So let's use the graphing calculator to figure out what that is now. I want it. Keeps opening the same window. Oh, it's switching tabs. Do. And this time our f of x is 2 times e to the 3x plus x. So that's what it looks like. And it looks like my 0 is right here at x equals negative 0.477. You could just read the graph and say, well, Desmos says that that's my 0. But we want to show it that that's 0 using the intermediate value theorem. So we said, let's look at f of 0. We calculated that that was 2. We did that on paper. Look at f of negative 2. We calculated that and we found that it was approximately negative 1.995. Now let's look at this on paper. So my function passes through this point, which is x equals negative 2, y equals approximately negative 1.995, which is about negative 2. And then the function also passes through this point, x equals 0, y equals 2. So I don't know what it looks like without my graphing calculator, but I know it's going to be continuous and it's going to look something like that. The question is, does the function ever equal 0? Well, if the function's continuous, then it does. There is an x value on this interval. It looks like it happens right there, where the function is equal to 0. Now, if you're saying, okay, let's make sure we're using the theorem properly. It says, use the theorem to show that this has a solution. Well, what do we need to know? Well, first of all, the function has to be continuous on the interval of interest. We'll say, since f is the sum of an exponential and polynomial function, and we know exponential functions are continuous, and polynomials are continuous. That tells us that f is continuous. And it's continuous where both of these are continuous, and they will have to be continuous at the same time. That's on the entire real line. So we know that that's true, and f of negative 2 is negative, and f of 0 is positive. So our 0 value on the right-hand side of the equation, that's our k, is between those two negative numbers, between approximately negative 2 and 2. Since our k is in between those two values and the function is continuous, then we have to pass through y equals 0. And again, y equals 0 is the x-axis. So the theorem says that provided all those things is true, then we get the function has a solution, or the equation, excuse me, has a solution. On the interval of interest. And the interval that we came up with was negative 2, 0. Now, this says use the bisection method to actually find the 0. Well, I know that the function has a solution, or I keep saying that wrong. The equation has a solution on the interval from negative 2 to 0. I just don't know. Is it between negative 2 and negative 1, or is it between negative 1 and 0? That's what we call the bisection method. We take this interval that's 2 units long and we split it in half and we say, okay, we know that there's a 0 somewhere in here. Let's see what happens at x equals negative 1. If that negative 1 value is, or if the function value at negative 1 is positive, then we know that the 0 has to be on this side. If the function value at negative 1 is still negative, then we know that the 0 has to be on that side. And so we'll do that. So that's for a different problem. Sorry. F of negative 1 is 2 times e to the negative 3 times negative 1 plus x, which is negative 1. And I don't know what that is. but I can figure out what that is using the calculator. Okay, so let's find f of -1. And we see that that's negative 0.9. So it's negative value. Let's plot those points. We had 0, f of 0. Label it. And then we had -1, f of -1. Label it. And then we've got -2, f of -2. And if I look at those vertical lines, x equals -2, x equals -1, x equals 0, I can see that the function values here between x equals -2 and x equals -1 are all negative. They're below the x-axis. So those aren't the function values we're interested in. We're actually interested in the 0, or we're interested in this 0 value, which is in between these two vertical lines, between the green one and the white one. It's right there in between. So you say, okay, it's not, or it's definitely in the right interval as opposed to the left interval. Let's focus on that left interval. We're still trying to find the 0. We actually kind of know what the 0 is. It's right there. We know it's -0.477, but we want to prove it. So we'll say, okay, I know it's on the interval from -1 to 0 now. Let's find out what the function value is at -0.5. Say, oh, that's very small. Let's plot that point, -0.5 and f of -0.5. Way too many negatives there. There we go. And that's close. That looks like it's almost, it looks like that might even be our 0. It's not quite right, but maybe we should zoom in a little bit. See, it's a little bit lower than that 0 line. And we know that that y value is approximately -0.5. So the y value here is -0.5. We know the y value over here is 2. And so we know that our 0 is between -0.5, or excuse me, between x equals -0.5 and x equals 0, which is the x value over here. And we can see on the graph that the answer is -0.477. You can say, okay, you could subdivide again. We know that that's, we know that the function is equal to 0 somewhere between -0.5 and 0. Since we know that just from looking at it, that it's likely to be on the left here, we could evaluate the function at the number that's like right in between -0.5 and 0. So you can go f of -0.25. And then plot the point. And it's not really getting us that any closer, but you can see that the y value has to be, or the x value has to be between -0.5 and 0.25. The y values are sort of getting closer together. But you can keep doing this and eventually you can get to the 0, or you could just use the calculator. And you see the calculator tells us that the answer is negative, or the x value that we're interested in is approximately -0.477. And that gets us where we want to go. So just to summarize, if you know that you have a 0 on some interval, you can split that interval in half and then figure out whether the 0 is in the left half or the right half. And then you can do that again and again and again until eventually you get closer and closer to that 0. Or you can just use a calculator, which is nice and easy for this particular function. But let's review the intermediate value theorem again. This video is supposed to be about this theorem. And the theorem just says that if f is continuous on a closed interval from a to b, and the function values at a and b are not the same, so you get two different y values, and there's some number k in between a and b, if the function starts here and ends here, it has to cross through this horizontal line y equals k. And when it crosses through that horizontal line y equals k, well, there's a point of intersection, that x value that corresponds to the y value y equals k is the solution to the equation f of x equals k. So the formal statement of the theorem is, then there exists at least one c in the interval from a to b such that f of c equals k, which again is just saying that the equation has a solution. We get at least one. So we might have one solution like we did in each of these cases, or in this case, or you can have like 6 solutions, you can have a lot of solutions. So the theorem just talks about that solution existing. And ways that this theorem may not apply is if the function's not continuous on a closed interval from a to b, if we're on an interval that does not include the endpoints, if f of a and f of b happen to be the same, all of those things would cause the theorem to not apply. Or if we're interested in an interval from a to b and k is outside that interval. We're interested in the interval from a to b if f of a is 5 and f of b is 10 and k is 15. Well, the theorem guarantees that we're going to have all the y values between 5 and 10 because we know that the function has to go from y equals 5 to y equals 10. But it doesn't say anything about what happens after y equals 10. It doesn't say anything about what happens below y equals 5. So we can't be sure of what will happen. Now, it might happen that our function, if this is, say, 5 and 10, of course, this is not to scale, and that's 15. It might happen that the function is continuous and the equation f of x equals 15 does have a solution, but the theorem would not guarantee that in that case. This is, I don't know, I'm just going to call that A and that B. The theorem just tells us that we're guaranteed to have all of the y values between 5 and 10 on our graph because the function's continuous and we start here at y equals 5 and we end here at y equals 10. But anything outside of that interval is not guaranteed by the theorem. Hope that makes sense. Let me know if you have any questions. And also, students, you're going to need to know how to summarize the theorem and then solve a problem. That's pretty much how your quizzes will go. So make sure that you can put this in your own words and you can think of some examples when the theorem doesn't apply and that you can use it to show that various equations have solutions, whether you're given the interval or whether you're not given the interval and you have to come up with one yourself.